Okay, so here I want to describe the concept of the deformable elastic network restraints, DEN restraints, which are basically explained in much more detail in these two papers here. And so the motivation for this came from the problem of refining protein structures at very low resolution. So let's say in this example here you have a starting structure. It could be a crystal structure or a homology model in some conformation, and now you have low resolution data, low resolution density map in a slightly different conformation. So here, let's say this is very low resolution. It's a 10 angstrom structure, and you see that this structure doesn't really fit into the density map. So now you want to optimize and refine your structure into this low resolution density map. But the problem is, if you do this by just regular refinement approaches, you will see that a lot of the internal structure that you had initially, like all the secondary structure, like the helices and some beta sheets, they are basically gone. They're broken because the 10 angstrom density map doesn't tell you anything about the hydrogen bond somewhere. So that's of course a problem. So ideally you would like to keep a lot of the information that you already had in your starting structure, and just optimize those features in the structure that you need to change to fit the data, but not more, basically. So as I said, the standard refinement basically yields a bad structure. And the question is, how can we make use of this prior structure information that we already have in the beginning? So this deformable elastic network, as I just said already, so the idea is that we want to refine only those degrees of freedom in our structure that need to be refined to fit the data, but not more. Or in other words, we can say we want to find kind of the relevant degrees of freedom for which the data actually provide information, and then only fit those and keep everything else similar or very similar to the known structure. So here's how we do this. We first of all set up an elastic network, and again, so elastic network doesn't mean we calculate normal modes or anything. So this has nothing to do with normal modes. The elastic network consists of randomly chosen distance restraints in the structure. So we pick two atoms randomly, and if they are closer than a certain distance cutoff that we choose, something like between 10, 15 angstrom, something like this. So if the two randomly chosen atoms are closer than, let's say, 15 angstrom, then we define a distance restraint there. And we do this all over the structure. So in this example that I've shown here, we have our starting structure is like this more extended helix, and this is the density map. And now, of course, we want to refine the structure into the density map, so we need to move these two small pieces of the helix into the density map. So now what you realize is that basically these two little helices here, they fit very well into the density. Yeah, you don't have to change these pieces at all. The only things that you have to change are basically a few degrees of freedom here and in the loop. So if we throw in all these distance restraints, this defines our elastic network. That potential allows, of course, some variation, but it's an harmonic potential, so this variation has some limits, of course. If we look at one specific distance here, like this in the kink, that needs to be kinked here in this loop region, and plot the energy versus the distance between the atoms. So in our starting structure, the harmonic potential looks like this. So this is the distance restraint in the starting structure here. And this point here is actually exactly the distance between these two atoms in the starting structure. And now when we refine the structure and we have these elastic restraints in place, it means we cannot move very far. So what we're doing now is we allow these distance restraints to adapt. So if there's if a certain distance feels a strong force from moving the molecule into the density map, then we allow that distance restraint or that distance to move even further. And we do this by making this this equilibrium distance here, so the minimum distance of the potential, we make this adaptable, or we can change that distance. So in this case it needs to become smaller, so this is a larger distance in the beginning, and to fit the density this distance needs to be become smaller. So we allow this distance to become smaller, and this red curve here is now the deformed elastic networks, the deformed distance restraint. Now it's the minimum of this potential is at smaller distances, and this is the adapted form. And of course, if we allow the minimum distance to adapt to any point, then we will very quickly forget about our reference model, our starting structure. Then everything can drift away, and all the information about these distances here will be gone. So what we're doing is we are coupling the minimum of this potential always with another potential, basically, to our reference positions or reference distances. And the strength of this coupling here is determined by a parameter which we call gamma, the gamma parameter. If we make the coupling very strong, then we cannot move very far from our reference structure. If we make this coupling very weak, we can basically refine to any structure we like. Of course, we want to fit the density, but at the same time, we also want to keep as many structural features from our reference model as possible. So we have two main parameters that are important here. The one is this gamma parameter, the coupling of the distance restraints to the reference point, and then also the weight. So what we're looking at is now a target function that consists not only on the typical two terms that you always use. One is the term, an energy term that penalizes deviations of your model from the data that you measured. So this is a function that you of course want to minimize. It's a difference between model and data. And this is terms from energy terms from a molecular mechanics force field, like bond restraints, angle restraints, van der Waals interactions, and stuff like this. This all goes in here. And then we have this additional energy term defined by this elastic network potential. And of course, this needs to be weighted by this factor here. And this is another important parameter that you have to choose to optimally fit the structure. So if you do this, we can make the same refinement again, but now with the DN restraints, and you see you allow this large conformational change. Like, this is not very, this global conformational change is not very large in this case, but it's a kind of collective global conformational change, while you keep all the internal distances intact, so the secondary structure is basically pretty much in place. But you don't have to choose yourself where secondary structure is. This is kind of taking care of the network, the deformable network. And this plot here shows the effect of the gamma parameter. So I did this refinement here with density maps at different resolutions, from 20 angstrom all the way to 3 angstrom, so very high resolution. what you're seeing is that if you use a gamma parameter as 0, your coupling is very strong, so you will stay very close to your reference model. If you use a gamma value of 1, you basically forget completely about your reference model. You can fit anything, and then the refinement is super flexible. So there's typically an optimum somewhere here. At the 20 angstrom map, it's very pronounced. Is the optimum gamma value in this case would be 0.8, and you see also that there is a slight shift in the gamma parameter. So if you go to higher resolution for the 3 angstrom and 4 angstrom map, for example, the gamma parameter would be a bit higher, and that's of course understandable. So this is the best gamma parameter, I should say. We plotted here the RMSD towards the correct structure. This is all simulated data. So this shift is understandable because at low resolution the density map does not provide so much information. So your gamma parameter should be lower. You stay closer to your reference model. You use more information from the reference. But if your resolution is much higher, then you can weaken your restraints a little. You can make your network more deformable and use less information from your reference model and use more information from your density map. So that's a typical situation. You have to kind of find the optimum gamma parameter and to basically balance experimental information and prior knowledge in form of your initial or reference model. Okay, so we typically optimize these parameters using cross-validation approaches, which is for X-ray diffraction very well established by the use of the R3 factor, and in cross-validation in cryo-EM we do a little bit differently, and this is something that we have also developed, but I'll describe in a different video. So the DN restraints are not only used in refinement in cryo-EM, so DN restraints are, for example, implemented in DIREX, in our real space refinement program DIREX, but it's also used for X-ray diffraction, and there's a few programs where the DN restraints are implemented. DN restraints are in CNS, starting from version 1.3, and then also in Phoenix since version 1.8. DN restraint or the DN refinement is also available at the SP Grid portal, so you can upload your data and your model there, and then run the optimization and gamma optimization, for example, through this SP Grid computing portal. Just the details are about this portal are described in that paper here. Okay, thank you.